So I am based in the University of Edinburgh, and well, my work is going to be, as the title suggests, on high-dimensional inference for extremes. So I work on extreme value statistics, and just to give you a sketch of the talk, so I've got an introduction including some motivation, with an application really to pharmaceutical extremes, which I find quite interesting. Well, the traditional approach to extremes is in climate science or in finance, so I always find it interesting when new applications crop up. And then I will move on to the study of multivariate extremes. So in particular, I will just touch briefly the max stable distribution world, and say I will discuss and justify approaches for multivariate extreme value modeling, which I find interesting from the viewpoint of, dimension reduction techniques. In particular, I will focus on the conditional approach to extremes, where it is possible, it is feasible to incorporate some graphical structures and sharpen inference. And I will describe, say, a type of methodology on how to do inference, and illustrate some simulation results. So please, any questions, just feel free to ask. So the motivation usually comes from the fact that we'd like to study phenomena that are rather unusual. So, for example, in environment, we might want to consider earthquakes or floods, heat waves, natural disasters in general. Or, say, in medicine, pharmaceutical industry, we might want to assess, say, the potential for drug toxicity. For example, we give an experimental drug in a clinical trial, and we might want to assess whether this particular drug can be toxic or not. Especially, we'd like to predict what will happen if we give, say, the drug to a more general population. So being able to estimate or extrapolate, say, from smaller samples is a key thing in extreme value statistics. And other type of, say, applications traditionally appearing in finance and insurance, where we can model large claims and say predict crashes or say losses. So the study of extreme value statistics starts with our usual central limit theorem, where we've got a bunch of IID random variables, say x1 up to xn, with some, say, common mean nu and finite variance sigma squared. Then we know that if we appropriately center and scale the sum of these random variables, we have convergence in distribution to the standard normal distribution, so written here by the Greek letter phi. So the extreme value analog of this theorem, say, looks now not at sums of random variables, but replaces the sum by the max, and tries to find, say, centering and scaling constants such that this probability here converges to a non-trivial, a non-degenerate limit as the sample size tends to infinity. So if this is the case, then we necessarily have a max stable law. So the only possible limits that can arise are of this form down here, where we've got G, a distribution function that is parameterized over a shaped parameter xi. And in practice, of course, we do not know what beta and what alpha is, so these norming constants are absorbed into the limiting distribution as location and scale parameters, and we, well, inference typically proceeds by estimating these via maximum likelihood techniques or, say, Bayesian approaches. It's usually a philosophical issue, but all the usual statistical machinery applies in likelihoods that are based from this particular distribution function. So the interesting thing is the shape parameter. This is the most interesting parameter because it dominates really the, well, extrapolations, mainly because it describes the tail behavior. So here is just a representation on, say, 3 different cases where xi is negative, xi is 0, taken as limit, and xi is positive, here showing short tail distribution for the first case, so that's the this dashed line, and then we've got, say, xi equals 0 to decay as an exponential, say, tail here with a solid line, And the positive case gives us, say, the dotted dash, which is effectively a heavy tail distribution, a heavy tail. So critically, all our extrapolations will be, say, affected by whether this parameter is positive or not. So having good methods to estimate xi is of key importance. So in statistics, the fundamental premise, well, in all statistical extreme value modeling, is that we can approximate the distribution of the extreme values by their limiting theoretical forms. Of course, the rate of convergence would always play a role here, but one typically hopes that the limiting distribution provides a good approximation to the observed extremes. So for example, here we've got, say, a bunch of IID random, a bunch of realizations from IID random variables, and well, we've blocked, say, the time index into several blocks, within which we have extracted the maximum with the red X here. So the right-hand side plot shows really the histogram of the max with the fitted extreme value distribution superposed. So in that particular case, it provides a good fit, and this is typically, or say, the traditional approach, the block maxima approach for univariate extreme value modeling. So based on the fitted distribution, we can actually, say, extrapolate and predict, say, the frequency of larger values. Right. So typical questions that we can address with extreme value statistics is, for example, what should be the minimum height of a dam so that, well, on average, the level of the sea will not exceed it, say, for 500 years. So, or in extreme value terminology, say we would like to estimate the 500-year return level, as it's called, or in, say, in pharmaceutical extremes, we might want to ask or assess whether a proposed drug is liable to incur deaths when it is marketed to the population, or estimate the probability of huge losses for a particular portfolio of stocks. So here's just an illustrative example of, say, an experimental drug that was given, say, to approximately 600 patients. So the patients were categorized into 4 different dose levels. So that's A, B, C, D, increasing dose level. And the experiment was as follows. So the patients came to the lab, and before taking the drug, we collected 4 variables, which are responsible for liver toxicity. So the variables are up here, so they've got strange names. ALT, AST, ALP, and TBL. I could all pronounce them in their Greek counterparts, but that would make it a bit uncomfortable. So the key thing to note is, well, here we're just plotting the scatter plot of the baseline ALT, that is before the drug was given to the patient, and versus the post-baseline, that is after the drug was given. So of course, in all cases, we've got a baseline effect, meaning that a patient coming to the trial with high ALT is more likely to have a high ALT in the post-baseline regime. So when modeling this particular kind of data, we would like to adjust for these kind of systematic effects. So these regression lines, so these are just some robust regression lines that, say, are used to adjust for this baseline effect. But if we notice more carefully at the points here, we see that as we increase those, there is something happening down here. So this strikes our attention into, say, checking whether there is heavier tail in dose D, for example. So in standard practice, one typically tries to estimate the probability that the ALT, say, or the AST, or either of these variables, exceeds an upper limit of normal, which is normally given by FDA, and it's just a high quantile. So here we're estimating, based on extreme value models, say the probability that the ALT will exceed an upper limit of normal, or it will exceed the 2 times 5 lots of the ULN, and so on and so forth. So what we get to see here is some preliminary evidence for dose-response relationship in ALT. Okay. So in other words, if we look at the 1,000 patient return level, that is the level that is expected to be exceeded on average once in 1,000 patients, we get a clear dose-response relationship for doses. So this was actually a nice study that we will try to formulate and develop extreme value models for estimating toxicity in clinical trials, drug toxicity. In particular, it's liver toxicity. But of course, the problem is not just univariate. It really depends on more than the ALT. So in particular, the FDA suggests that a combination of extreme values is responsible for liver toxicity. The guidance actually suggests that if ALT and TBL jointly go high, while a third variable, the ALP, stays at some moderate levels, then there is some clear indication for liver toxicity. However, we know that this particular drug is toxic, right? And we did not find any relationship with ALT going high jointly with TBL while ALP was staying moderate. However, what we did manage to find was some quite strong relationship with ALT and ALP as dose increases. So here I'm just plotting the some residuals ALT and ALP after removing some systematic effects and trying to see what happens as we condition on one variable being large. So obviously there is some relationship here with dose, and this kind of strikes or questions really the validity of the FDA suggestion. Should we look at other combination of extreme values as well? It's probably a good question to ask, or it's probably a good question to check at a multivariate level if we actually consider all the variables into the problem. Okay. Right, so this was just an introduction to some pharmaceutical extreme value modeling. As I suggested, it's usually the case that problems in practice are more than one-dimensional. In particular, they're multivariate. So from now on, I will focus attention on say, the multivariate extreme value modeling. So in particular, I will start with the traditional approach, which is component-wise maxima. It's an analog of the block maxima approach that we initially saw. So if we start with, say, bold X to be a d-dimensional R plus valued random vector, say with some specified Frechet margins, this is something that we can do without loss. Then we know that, well, if we actually take the component-wise maxima from, say, n realizations from this random vector, we know that this vector here, yn, the vector of the scaled component-wise maxima, will converge to, similarly with the univariate approach, to a max stable law. So now yn converges to a bold y, a d-dimensional vector which has also unit Frechet margins, and admits this representation. So its survival function is the exponential to the minus this integral here, where in this integral we've got a measure h. So that's just think of it as a distribution function that lives on the unit simplex. So so h actually is a measure. It's called the spectral measure, and has total mass d and satisfies some moment constraints to be consistent with the assumption that it has the given margins that we impose. So these actually are the only constraints that h has to satisfy, which means that h can be really arbitrary, right? So if we compare it with the univariate max stable law, which is fully parameterized, in the multivariate setting, we don't have nice, simple parametric forms for h. Of course, one can construct parametric models, right? But they will not be necessarily general to, say, capture the full dependent structure that could be potentially encoded in h. So h actually encodes all the information about the dependence of the component-wise maximum. But Of course, this is a restrictive issue for modeling, but what is more restrictive is some additional restrictive dependence assumption that this distribution imposes. So if we say have a bivariate vector, max table, say follows a G, here max table distribution, and we define, say, this coefficient of extremal dependence, chi. So chi is a probability that yj will exceed u conditionally on yi exceeding u, and let u go to infinity, to the upper end point of the distribution. Then we've got two different characterizations. Of course, it's a probability, so it will be between 0 and 1. And if it's positive, the dependence is termed asymptotic dependence. Whereas if it's equal to 0, the dependence is characterized as asymptotic independence for this particular distribution. Of course, max table random vectors are asymptotically independent if and only if the distribution factorizes. That is, when they are exactly independent. Okay? So this imposes some restrictive assumptions in the way that the dependent structure of the observed extremes must be compatible with the limiting model for the extremes that have not been observed. Okay? But that's not necessarily the case. The classic example is the multivariate normal distribution, which is, say, in this particular case. So the multivariate normal distribution, the component-wise maxima from the normal are asymptotically independent, right? But at any observed level of, say, realizations from multivariate normal distribution, we will see some marked dependence. Right? So fitting, say, max table laws to the component-wise maxima of normal vectors would impose, say, asymptotic dependence. That is, it would impose some additional, say, dependent structure for the extremes that have not been observed. So it's critical for extrapolation. And another example of asymptotic independent vectors is, say, the inverted max table. So if we start off with, say, max table vectors with unit Frechet and define, say, vector algebra to be interpreted component-wise here, x to be 1 over y, then y has unit exponential margins. It's called the inverted max table random vector, and also it's parameterized according to the same type of, say, dependence function we had before for the max table vector here, and is asymptotically independent, a fact that is can be found from the joint tail down here. Right. So, just a pictorial representation of how asymptotic dependence and asymptotic independence look like. So the left plot shows realization from a max table, from bivariate max table vector to exponential margins. So we see some strong dependence along this, say, diagonal axis. So whenever we condition on, say, the x variable being large, there is positive probability that the y variable will also be large. Something that doesn't hold when we flip the max table vector. So now the lower tail of the max table vector becomes asymptotically independent, meaning that the mass drifts away from the diagonal as long as we condition on levels of the x variable being larger and larger. So here comes into play the condition limit laws, first proposed by various people, including Hefner and Tone, but formulated strictly by Hefner and Resnick. So Sid has played a crucial role in understanding the condition limit laws. It has provided groundbreaking theory, actually. So what the condition limit laws are, so we start again with some d-dimensional random vector x, and suppose we fix it to have exponential margins. So the condition limit laws assume the existence of, say, some centering function a that maps to r d minus 1 and scaling function that maps to r plus d minus 1, such that, say, conditionally on just one component of this random vector being large, right, the centered and scaled concomitant vector here converges, jointly with this excess random variable, to a product distribution So since we've started with exponential margins, this guy would have here an exponential tail times, say, the distribution function of this guy conditionally on xi exceeding a large threshold. Right. And why is this important, if the case? The importance comes from the fact that it actually captures asymptotic dependence and asymptotic independence in a single modeling, in a single formula. So if we have max stable random vectors, we know that when we center them by just x1 here, say without loss, I'm just conditioning on one variable, on the first variable. So the vector without the first component centered by x1 will converge to non-degenerate law. Similarly, for the inverted max stable random vectors, something that so that's part of my contribution, is that when we appropriately center, say this guy here with x1, say we subtract some multiple of x1, where this guy here is just bounded by 1, and divide, say, by some power of x1, will also converge to a non-degenerate law. Or similarly, if you like to think about standard Gaussian vectors, say if we subtract, say, the correlation squared x1 and divide by x1 to the power, root it, sorry, we know we have convergence as u tends to infinity to the multivariate normal vector that does have this covariance structure here. So sigma given 1 is really the conditional correlation matrix, which is just just meets this form down here. So so there are some points I would like to reflect in this case, is that we've got limiting theory that actually encapsulates both asymptotic dependence and asymptotic independence according to how these parameters, say alpha or beta here, look like. So if alpha is 1 and beta is 0, we have, say, asymptotic dependence. Whereas if alpha is less than 1, we've got asymptotic independence. What is also interesting is that if we start with some graphical structure, say in the Gaussian world, which is encoded in the correlation matrix sigma, this would still be preserved in the limit. So the limit distribution here would also have the same graphical structure. So this opens up possibilities for using graphical modeling in the conditional approach. So this motivates a statistical model. So for large U, we can regress the concomitant vector here on xi subject to xi exceeding this U. Okay, so the coefficients here, alpha and beta, are just d minus 1 dimensional vectors. These are the parameters. Okay, and bold z is just the it can be thought as a residual random variable that follows this limiting law. Of course, in theory, this limiting law, k and kappa here, can have actually any form. For example, in the Gaussian case, we've got a multivariate normal, whereas in the max stable, we've got something different, or something different in the inverted max state. So there appears to be a complication in terms of modeling this guy down here, but there are ways to overcome this problem. So we've got parametric structure for norming functions a and b, given by, say, the vectors alpha and beta, where each component of the vector alpha and beta is in this space. So alpha is actually a slope parameter, and beta is a scale parameter, is a variance parameter. And they actually capture the dependence of the component in that vector with large xi. Additionally, we've got dependence between these components given xi being large, which is captured by this law here. Okay. So in the bivariate representation, it really looks at a semi-parametric regression model where y is regressed on large x in this type of form. Okay. And inference proceeds by, using a false working assumption. Okay, of course it's false. It's false to assume that the residual vector is z, is multivariate normal, but it's a perfectly working assumption due to the fact that it yields consistent estimates. Okay. And then inference proceeds by non-parametric estimation of z via the empirical distribution function or some kernel density estimation. So we need to do non-parametric estimation because this z here can be anything. So once we get consistent estimates alpha hat, beta hat, we form the residual z here, and we estimate its distribution non-parametrically. Of course, as dimension increases, the empirical distribution function does not scale very well.
Could you back up? So you do something like a Gaussian likelihood, even though you may not believe it's really Gaussian.
It's like a regression, yes.
And then you just do maximum likelihood.
Exactly. I mean, you can either it's like regressing. It's like a standard regression, ordinary least squares. However, if you want to be more robust, what you can do is you can change this multivariate normal to a double exponential, which would give you an analog for the median regression. So you can be fairly robust in this situation. Or you can, well, there are several modeling, there is a whole range of modeling possibilities for this particular piece here.
And is it obvious why you're getting consistent estimates this way?
Well, it's not obvious, but it can be proved.
That it's true.
Yeah, it can be proved. Yeah.
All right.
Okay, so we are cursed by that dimensionality, obviously, when we are relying on kernel density estimators. So some part of the talk today is on graphical modeling and ways to overcome, say, this curse of dimensionality, effectively by studying Markov structures like graphical models and say factorizing the distribution of Z into, say, the product of some lower dimensional distribution, which can be then estimated more efficiently, again using some kernel density or the empirical distribution. So how do we estimate things from the model? So here's the simulation algorithm. So first we start with xi. So we simulate an xi from a unit exponential distribution conditionally on xi exceeding u. And then we sample independently, say, a z from the empirical distribution function or any model that you might want to put, say, on the distribution of the residuals. And set, say, the concomitant, say, vector to be given by this form. So repetition of the algorithm gives you a Monte Carlo type of simulation algorithm, which you can effectively use to estimate any functional. So we can actually estimate the probability that the vector x will live in a set C, given that any ith component is large, as the long-run proportion of the samples that fall in that set. Of course, we can also get the uncertainty by implementing the same type of algorithm via bootstrap procedure. Okay, so I've been talking about graphical structures and Markov processes. So here's some study on Markov processes. So of course, in the Gaussian case, as we saw, if you put any correlation matrix sigma, you will result with the same correlation structure into the limit. Okay, so our question is, what happens when you move away from the Gaussian world? So the inverted max table world is a nice world to study asymptotic independence, mainly because it gives actually a whole range of models based on which you can explore, say, the assumption of graphical models. So if we start, for example, with a first order chain, so we've got a conditional independence graph here, Markov, and assume that the bivariate margins are inverted max table. Then we get, say, well, for a segment from this process, we get that the normings here decay as a power. So the first, say, lag. So if we condition on the first instance being large, then we need to scale, say, the second variable. We need to center it by alpha x1 and scale it by x1 to the beta, and then we've got some power decay that goes to alpha squared up to alpha d minus 1 for a d-dimensional segment. Okay, so compare this with the multivariate normal, which is type of the same power decay. Of course, when alpha is 0, all the structure is absorbed into the other norming function. So now the betas scale as a power. Okay, so the question is what happens for higher order Markov processes? So when we've got this canonical class, which is parameterized by the alpha and the beta, we notice that all the structure is absorbed in the dominating norming. And by dominating, I mean that when alpha is positive, then alpha x1 will always dominate h1 to the beta because beta is less than 1. So when we've got alpha is 0, then the structure is automatically absorbed into, say, the scaling function. Right. So what we could do is we'd effectively exploit, say, the structure in the higher order case, but just studying the simplest example, which only uses centering. Okay, and see what, for example, the second order Markov process assumption imply for the norming. Okay, so this is something that took me a while to figure out. It's probably more than a year, but here how it reads. So we've got a second order Markov process. So here's my segment from it. So it's x1, x2, up to here x5. And we condition on the first component being large. So we assume, say, that the trivariate margins are inverted max stable, okay, and that we have stationarity. So the distribution of this triple here, x1, x2, x3, is the same with the distribution of x2, x3, x4. Okay, so if we start, say, with x2, we need to center it by, say, a corresponding coefficient here, alpha xy, that relates, say, the distribution, if we read as x, y, and z, it relates to the distribution of y given x. Fine. So when we go to the next step, x3, we need to look back at 2 times, x1 and x2, and pick the dominating norming. So since this alpha is always less than 1, we pick the dominating norming to be this one. And we couple it with the time point that we're currently in. So that's, well, if we read x, y, z, that needs to be coupled with, well, we need to enter the coefficient of the conditional distribution of z given x, not x, z. So now we repeat the same process. We go to x4, reading again this vector as x, y, and z by stationarity. So we need to look at 2 time instances back and pick the dominating norming. So by assumption, alpha xy is greater than xz, so we pick this guy. Okay? So we need to couple it with the time point that we're currently in. Okay? So that's z given x. So we have an alpha xy coupled with an alpha xz. And so on and so forth, we get the decay of the norming. So similar type of thing the other way around. Actually, it's a similar kind of thing when we've got a third order Markov process or a kth order Markov process. And what is the beauty from here is that we can actually explore it. We can explore Markov processes on directed graphs. So here's just a picture to show you how the decay of the norming looks like. So it again decays as a power, but maybe better described as a lagged power, lagged by 2. So here we've got, say, the decay of the norming for the first order Markov process, whereas here it's just the second order, the solid line is the second order Markov process. So decay somewhat slower than the first order one. And if you would like to see, say, realization from this process, so that's just a typical realization on the left-hand side plot, whereas here it's just conditionally on the first component being large. So we're interested in understanding what happens to the process when we condition on an extreme event. How does it actually drift back to the main body of the process? Okay, so here's something that's, say, newer. So what happens actually in first order Markov processes in space? So when we've got directed graphs. So here we've got a lattice, okay, and we've got the nearest neighbor structure, and I'm just conditioning on the x11 variable, so 1, 1, say I'm starting counting from this corner here, so I'm just conditioning on this being large. So we've got, say, 2 coefficients here, an east and a south. So if we want to read say what the norming is at this point is just the shortest path from this corner. So that would entail, say, 1, 2, 3 moves east and 1 south. So you can always do it at 1 south from here and then 3 moves east. So you again get the same picture. Similarly, we can study directed graphs of this form. So when we add, say, a type of northwest to south this direction, so if we condition now on the center of this lattice, say if we've got variables sitting on these vertices, and we condition on this one being large, we again get, say, a shortest path type of structure. So here, if we want to read what this coefficient should be, then we go just one step. Well, we need to go the shortest path, so we need to go one step northwest and then 1 west. Or in other words, if we just plot the contours of these models, say respectively here when we condition on the top left corner, we get, say, power decay that has this particular form. And when we include a directional effect, we get a contour plot of this type of form, which is actually comprised by these, say, these lines, which is this power decay as before, and then we've got also these rectangular lines. So by adding more, say, edges, what we do is we strengthening the dependence. So if we add also a direction from, say, southwest to northeast, then we will get, say, just squares here, meaning that we've got stronger dependence. So the beauty of this is that it allows us to construct actually models on any kind of directed graphs. Okay, and the beauty is that these models are lower dimensional. Okay, for example, think of the first order Markov case. You only need one parameter, alpha, and this gives you the decay. Right? Of course, you need a beta parameter as well, but it offers a great dimensionality reduction. So just to illustrate the efficiency gain that one could have when, say, it uses a structured model. So suppose we generate data from first order Markov process. So this is just a preliminary simulation study I've conducted on Gaussian inverted max table and max table vectors, and estimate, say, for large x, the probability that, well, conditionally on the first component being large, the probability that the remaining component will be less than this vector x. So think of this probability as a function, say, of x. Sorry, that should have been an x here, and a function of the dimension. Okay, so we'll estimate this probability for several levels of x and for several dimensions, using actually the current approach. Just go straight with unconstrained parameters, or using a structured approach, which could actually impose a first-order Markov structure. So to use this structured approach, one goes to the multivariate normal likelihood and just optimizes the likelihood in a constrained way, constrained so that the parameters live in that space. Okay, and for the non-parametric beast, one actually simulates from the this particular density. So since we've got a first-order structure, we know that the density would be just the product of the first-step transition probabilities. So it offers actually dimension reduction in the parameter space here and in the kernel density estimation. So it's a two-way, it's a sort of win-win situation. So here's, say, a three-dimensional example. So the level x that I had before here, this level x is just this level down here. And on the y-axis, I'm just plotting the probability, the estimate. So the solid line is just the theoretical, the one I'm simulating from. And I've got two different lines. I've got a dashed and a dotted dashed. I don't quite remember which one is which, but it will become obvious in the next plot. And I've got some uncertainty, 95% confidence bands superposed around the estimate. So of course, in the three-dimensional example, we cannot do much. I mean, both approaches perform in the same manner, but as long as we start increasing the dimension, we see that the current approach scales, well, does not scale very well. So, meaning that the uncertainty increases as well as the bias. And when we go to higher dimensions, of course we perform very well in this situation compared to the current approach. And it offers, again, the possibility for doing dimension reduction techniques and gains in efficiency. Okay. I think I'll put a full stop here and let you actually have any questions. Thank you.
Any comments or questions?
So is it, just based on this very last point, is it worthwhile in some situations where you don't have the graphical structure, imposing it anyway?
Yes,
Giving biases
of course,
values?
of course. Well, in practice, you don't actually have. You might want to learn the graphical structure, which would add more uncertainty to your problem. But simulation suggests that even when the structure is more complicated, you can still gain by just, for example, using a nearest neighbor approach. So yes, you can do a whole lot better. That's a good point.
So in the that theta of x, I mean, one way to reduce the dimension would be to replace x2 on out by the maximum, since you had the same x as the upper bound anyway.
Say again, sorry. In this last point? Yeah.
So take the maximum of x2 and xd, and then you'd have two dimensions.
Yes, of course. That's.
And how does that compare? It works? Or doesn't?
I haven't checked, to be honest, but it's more about well, this is more to illustrate a one-dimension. Well, in principle, we will not necessarily estimate this probability for same x. Okay, but if I change x, I cannot picture it, of course. So it gives me a nice way to, for presentational purposes at least. But it's a good point you make. I haven't really checked how it would compare with the max, but I know that as long as I start playing with the x's here, I'll get the same type of pattern as these guys here. But of course, I understand that modeling just the max from these variables would reduce the dimension.
And with the graphical models, is there some way of discovering what the right graph should be? That's probably hard.
It's
but
a good question.
There are these Vine copula models.
Yeah.
Related things.
Yeah. I'm not sure, to be honest, but I think it's a good point. It's something I haven't really checked so far, because I'm really thinking of imposing a structure other than estimating first. But of course, one would like to do it jointly. Yeah. But I've seen recently a paper on Vine copulas and extremes, which was intriguing and interesting.
Anybody else? Do we have snacks?
Yes.
Okay, there are snacks, I guess, in the usual spot, just in case Shane hasn't eaten enough today. Thanks very much.
Thank you.